Okay, now we're going to apply these same ideas to analytic geometry. Analytic geometry are geometric concepts applied to geometric space, or in this case, a plane. We'll talk about planes later. So we take the coordinate plane and we've drawn a line segment. Line segment PQ is right here. It has endpoints P and Q, and it is a line segment running between the 2 points. And so we're going to ask a few questions here. The first two we're going to ask are, what are the coordinates of P and Q? Note we just gave the letter P. We didn't say point P. We just said P. When we say just the capital letter P, we mean point P. All right, so point P has the coordinates, the bivariate coordinates. X is 2, Y is 1, 2, 3, 4. So P is at the point, parenthesis. Got to put the parenthesis. We don't just write 2, 4. We write parenthesis 2, 4, close parenthesis. That represents a coordinate on the coordinate plane. Point Q is at the point C. I'm actually going to go up here. I'm going to go to the y-axis and count over instead of trying to count over here. 1, 2, 3, 4, 5, 6, 7, 8. So that's 8 across. And then from here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 up. So 8, 14. Okay? Then we're being asked, what is the length of PQ, of line segment PQ? Okay? Now, to find the length of this, what we're going to do is we're going to use the Pythagorean theorem. We're going to create an imaginary right triangle. An imaginary right triangle. You can see now that that's a right triangle, and we'll talk about right triangles later. But anyway, you probably already know the Pythagorean theorem, even though we're in a geometry class here and we haven't talked about it yet. But this is now a hypotenuse, okay? And so we know if we call this A and this B, that means this is C, okay? And so essentially what we have here is the distance of one of the legs is 1, 2, 3, 4, 5, 6. The distance of the other leg is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The way you can get that goes like this. 8 minus 2 is 6. 14 minus 4 is 10. And so the way that we find the length, it's a distance. So we're going to use the letter D. So the distance, which is a hypotenuse, the distance squared is equal to 8 minus 2 squared. 8 minus 2 squared. Now note, because this is being squared, 2 minus 8 squared is the same. It's going to be a positive number. Plus 14 minus 4 squared. Now, when we do the square root to cancel here, that means we're going to do the square root of this whole thing, and it becomes the distance is equal to the square root of x minus x squared plus y, oops, I don't want to put y, I meant to put 14, y minus y squared. And then when we put this, or when we calculate this, we get 8 minus 2 is 6, 6 squared is 36, 14 minus 4 is 10, 10 squared is 100, and so we get 36 plus 100 is the square root of 136. That's the official answer. But now we're going to put it into a calculator, and we're going to get a decimal answer. We're going to go square root of 136, and we get 11.6619. We're going to go 4 decimal places here. So the length of line segment PQ is 11.6619. All right, now the last question we're going to ask is, what are the coordinates of the segment bisector of line segment PQ? We want to know what point breaks this exactly in half. Well, in analytic geometry on a coordinate plane, we call that the midpoint of the line, or the midpoint of the segment. And the formula for the midpoint is very simple. Add the two x's together and divide by 2. Add the two y's together and divide by 2. So in this particular case, the coordinates are going to be add the two x's, 2 plus 8, and divide by 2. Add the two y's, 4 plus 14, and divide by 2. And that becomes 2 plus 8 is 10. 10 divided by 2 is 5. 4 plus 14 is 18. Divided by 2 is 9. And so the point 59 is the segment bisector of PQ. 5, 9. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9. There it is right there. We'll call that point M. And that is how to identify the segment bisector of a line segment that is on a coordinate plane.